Let's talk about how to balance redox reactions. I've written a very simple redox reaction up here, and that's the reaction between copper metal and silver ions that are dissolved in solution. When you combine these two um, chemicals together, you will form, the silver will actually oxidize the copper, and the silver will be reduced to silver metal, which will come out of the solution, and then the solution will start to get blue as the copper oxidizes inside. And this is a fairly simple reaction to balance. In fact, you can probably do it just by looking at it and noticing that I need 2 silvers for every copper, because this is going from a copper 0 to copper plus 2. That's 2 electrons different. And this is going from a silver plus 1 down to silver 0. That's 1 electron different. So we're going to need 2 silvers and only for every copper. But let's go through a way to systematically balance a redox equation, because coming up we're going to need a little bit more help when things get a little bit more complicated. And so what we'll do is we'll split this apart into 2 half reactions. So just the copper portion of the reaction, and then just the silver portion of the reaction. So if we do that, we'll get something that looks like this. Copper goes to copper ions. And to balance this equation, we just need to make sure that all of the atoms are the same number of atoms on both sides. There's 1 copper, there's another copper there. So we're done with that. And then we need to balance the charges. Now there's a 0 right here, and there's a 2 plus there. So we'll just simply add some electrons. We need 2 of them because there's a plus 2 here. There's 0 charge over there. So 2 plus minus 2 electrons, that's 0 on both sides. This is now a balanced half reaction. And in this case, it's the oxidation portion of the reaction, because the silver went from 0 to plus 2. That's an increase in oxidation number, and so that is oxidized. And put another way, this is the reducing agent, because it's what caused the silver to be reduced. Let's do the other part of the reaction. So we have silver ions going to silver metal. So there's a 0 there. So in this case, we have a 0 charge on the product side. We have a plus 1 on the reactant side. So we're going to need to add 1 electron to our reactants to reduce the silver. So this is the reduction reaction, and that would be the oxidizing agent. So this is the reducing agent, this is the oxidizing agent, this is the reduction reaction, that's the oxidizing reaction. Things can get a little bit complicated, but just think about what's happening, and we'll put it all together. Now, when we want to put this together to equal our equation up here, we'll simply add these together in a way that the electrons will cancel. So I notice that I have 2 electrons here and I have 1 electron there. Well, I actually need all of the electrons gone from my final equation. So I'm going to multiply everything here by 2. And that will make sure that I have 2 electrons to cancel when I add these all up. So in the end, I will get, and I'll just write it up here, 2 silvers going to 2 silvers there. And now this is a balanced equation. Now, that was something that we could probably have solved just by looking at this top equation. But let's move on to something else. In this case, the reaction didn't involve any hydrogen or oxygen or other things in the solution, but some reactions do. And here's an example of that. We have zinc metal reacting with this vanadium compound ion oxidize the zinc into zinc 2 plus, and then here's the vanadium. So the vanadium must have been reduced because the zinc was oxidized. Now, this is done in an acidic solution. And what that means is you might notice that there's no oxygen on the product side to balance this. So you might initially think, whoa, we can't balance this equation. There's no oxygen over here to balance it. It's just a little bit hidden right here in the aqueous symbol. Right there, there's oxygen in the water. And in this case, we have an acidic solution. So we really have H plus and we have water to work with so that we can balance our oxygens and hydrogens, whatever might come up in the solution. So let's again balance this in two pieces. So we'll take the oxidation piece first. We have the zinc going to zinc ions. And I always like to start with the very obvious, easy one. And so, you know, just to get that one out of the way, and then I can look at less ions on the paper. So, like before, we have a zinc going to zinc 2 plus. It's very similar to the copper. This is going to require 2 electrons being made or released from this zinc. And then let's look at the vanadium portion, which is going to require a little bit more work. So we have this vanadium oxide, and then that's going to go to the vanadium 3 plus over on this side. Now, we need oxygen somewhere over on this side, and I said we have H plus and we have water to work with. H plus doesn't have any oxygen with it, water does, so I'm going to add a water to this side, and we'll see how much we need. So now I have 1 oxygen over here, I have 1 there, so I really just needed the 1 water in this case. Now, I have hydrogen over here, but I don't have any hydrogen in the reactants, so I'll have to add some in. And remember, this is acidic solution, so we have H plus to work with. How convenient. We need 2 H pluses on this side of the equation, so we'll just add that in. There we go. Now we can check to see if all of the atoms are balanced. I have 1 vanadium, I have 1 oxygen, I have 2 hydrogens. Excellent. Now we just need to balance the charges. I'll add them up. I have 3 positive charges on my product side, and so I will need 3 positive charges on the reactant side in order to get both of these sides to balance. Right now I have 2 here, and I have an additional 2 here, right? Because I have 2 H pluses. So that means I have 4 plus charges on my reactant side. So to get it down to 3, I'll simply add an electron to this side. Now, there is another way to figure out that we needed to add 1 electron to this side, and that is to calculate the oxidation number of the vanadium. You know, you'll notice that we have -2 for the oxygen, but this whole thing must be +2. So what -2 equals +2? Well, +4. So the vanadium is +4. And you'll notice that I went from a +4 to a +3. I should add the positive. And that is 1 electron different, and so I should know that I can add 1 electron here. And that's a good way to check whether you've done this right, or if you prefer, you could look at this equation up here and try to balance it just simply using oxidation numbers. But I find typically that it's a little easier to break it apart into 2 different reactions and then add them up later. Now, if you notice here, I have 2 electrons for this reaction. I have 1 for this one. So I will again have to multiply this reaction by 2 when I add them up to have the electrons canceled. So I'll just write that here. And so then when I add this all up, I will have a zinc metal plus 2 vanadium oxide. I guess vanadium 4, I could say. Plus 4 H pluses goes to a zinc ion plus 2 waters plus 2 vanadium 3 plus. And that will be the balanced equation. And this one would have been a little bit harder to just try to balance simply by looking at that. Now, you can imagine that if we can balance equations using in an acidic solution, we can also balance equations in a basic solution. And in this case, we will have water and OH minus to work with, or hydroxide, since we're in a basic solution. So, again, I'm going to take this and I'm going to split it apart into 2 pieces. I'll have my chlorine portion, right, the part that contains chlorine, and I'll have the part that contains chromium as my 2 pieces. Let's start with the chloride part. So, you'll notice that I have an oxygen on this side, and I don't have an oxygen on that side. So what do I do? Now, keep in mind that in this case, I can add water and I can add hydroxide to my equation. Now, which one has more oxygen on it? Well, you might say, well, they both have 1 oxygen on it, so I don't know why you're saying which one has more. Well, it's really which one has more oxygen on it per hydrogen, because there's no hydrogen up here. So when we add some hydrogen on there, we're going to have to add some water in somewhere to get the other part of the hydrogen to balance it. So we really need to look for which one has more oxygen per hydrogen. And that's hydroxide, because they're 1 to 1, whereas water has extra hydrogen on it compared to hydroxide. And so since that's the case, I'm going to put hydroxide on the side that has the lower amount of oxygen on it. And that will get me towards where I need to go. Now, I have a hydroxide over here, which takes care of the oxygen, but I'll have to add some water on this side to balance out my hydrogen, because I have to have a source of that somewhere. Now, you might notice that now I have an extra oxygen on this side, and I have 2 hydrogens, and I only have 1 over here. I can fix that very simply by adding in a 2 here. Now, in that case, I have 2 oxygens, 2 hydrogens, 1 chlorine. I have balanced the atoms on this reaction. But you'll notice that now I can balance my charges. And you'll see that there are 1, 2, 3 negative charges on this side, and there's only 1 negative charge over here. So we better add 2 electrons to the reactant side so that we can balance out the charges. So now I have 3 negative charges here, I have 3 there. This half of the reaction is balanced now. Now I can move on to the chromium portion. Okay, so I've written this out. Now I have the same amount of oxygen on both sides, but I have more hydrogen right here. So I'm going to put the molecule that I have of choice that has more hydrogen in it on the product side, because I'm going to need more over here, and that is water. right? Because water has 2 hydrogens for every 1 oxygen. So I'll be able to get more over here. Now, I've added some oxygen over here with my water, so I'm going to have to add some more hydroxide onto this side too. And you'll notice that every time I add a hydroxide, I still add another hydrogen, so I'm going to have to kind of compute that out, right? Now, I need 4 more hydrogens on this side than I have on that one. Each time I have the pair between the hydroxide and water, there's 1 hydrogen difference between the two. So I should be able to just say 4 hydroxides and 4 waters, and that will probably fix this problem. So let's see how we did. I have 8 oxygens on this side, and I have 4 plus another 4 there. I have 8 oxygens on that side. And now I have 8 hydrogens on this side, 4 there, 4 there. And I have 8 here, 4 times 2, 8. And then 1 chromium, I didn't change that part. So now we've balanced the atoms that we have on the page. Now let's balance the charges. There are 5 negative charges on the reactant side. There's only 2 negative charges on the product side. So we need to add several electrons over here. 3. And we could verify both of these things by looking at the oxidation state on this chromium versus that one. And you can verify this yourself, but the oxidation state on this particular chromium is +6, and the oxidation state on this one is +3. And so indeed we have changed by 3 electrons. And you can also see that in this chlorine up here, we're going from a, let's see here, that would be a +1 oxidation charge to a -1. So that's 2 electrons change. Now, when we combine these 2 reactions together, we must do so in a way that cancels the number of electrons. So we'll need to multiply this first equation, everything by 3, and this next equation, everything by 2. That will give us 6 electrons on there to cancel, and then we can add that up. So let's do that really quick. So this times 3, and everything in here times 2. Now you may also notice that we have some water on the product or reactant side and some water on the product side, and we have some hydroxide on opposite sides. We'll be able to cancel that out in a minute, but let's just get that what's added up written down first, and then we'll start canceling everything out to simplify it down so we don't get too confused. So we have 3 ClO negative plus 2 CrOH4 negative. Actually, let's figure out what's going to cancel out before I write it down, because I'm writing in kind of a pen here. So this will be 3 waters right here, and this is going to be 8 right there. So I'll just kind of write that down right up here. And this is going to be 8 hydroxides, and this will be 6 over here. So we're actually going to have 3 goes to 8. That's actually going to be 5 in the end. All right, because 8 minus 3, that's 5. And in this case, that will go away, and this will go down to just 2. So plus 2OH goes to 3 Cl minus plus 2 CrO4 2 minus plus 5 waters. And that should be balanced. We have 3 chlorides, and how many oxygens do we have? We have 3 there, and we have 8 there, and then, well, we have 8 there, so that's, and then, yeah, there's 5, and then hydrogens, we have 10 here, and we have 8 plus 2 more, that's 10. So we are indeed balanced. You can see how being able to split these apart into 2 pieces can really help us, especially when the reactions get a little bit more complicated.